impatient. Oh no, my heart can't fake it. Idolize you, 'cause you're always on my mind. He degrade you, I upgrade you. You shine like constellation. I adore you, appreciate you. Yeah, yeah. Ooh, you used to say you wanna trust yourself from ways to run away. Oh, every time you wear that dress, you fuck with my head. Fuck with my head. Those bright lights shining on you standing there. I just wanna give you all of my attention. You're my obsession. Those bright lights, love the way they make you shine. Told them that you needed space. Said you need some time to think. You're looking for a peace of mind. Tired of crying all the time. He left you standing in the dark, playing games with your heart. He don't deserve you now. I'll catch you when you're falling down. Ooh, you used to say you wanna trust yourself from ways to run away. Oh, every time you wear that dress, you fuck with my head. Fuck with my head. Those bright lights shining on you standing there. I just wanna give you all of my attention. You're my obsession. Those bright lights, love the way they make you shine. Trying to find the words to make you stay, to make you stay when you just wanna run away, run away, you wanna run away. You're trying to find the words to make you stay, to make you stay when you just wanna run away, run away, you wanna run away. Every time you wear that dress, you fuck with my head, fuck with my head. Those bright.
Good morning, everyone. Welcome back for the second part. And I would like to introduce Professor Alberto Burlina. He is the director of the Division of the Inborn Errors of Metabolism of the University Hospital of Padova. And he's also director of the Expanded Neonatal Screening Center of the northeast of Italy. He's a co-author of many international guidelines for diagnosing and monitoring of inherited metabolic diseases, but he has also a huge interest in the lysosomal storage disorders, and as they screen already for some years for those disorders, which he will tell you a bit more about it.
Good morning. Let me thank my friend François for the very kind invitation to join your society, and also because we share many meetings with François. We are a long time in the stage, and also we have a sort of parallel life. He is in Belgium, I am in Italy, but we are both pediatricians. We started to look at the metabolic disease many years ago, and also we understood the importance of the screening as a prevention. I prefer to call it prevention, not screening, of inherited metabolic disease. Well, how I will spend the next 20 minutes. I will just give you a very short overview of what is going on in the lysosomal world in terms of screening. And then I focus my attention on what they're doing in Padua, in the northeast part of Italy, just to remind that Padua is a city with a historical university background. It's very close to Venice. And then we have, I will show you as a pediatrician, the long term now, I can say, of screening for patients diagnosed by neonatal screening, and also give you some brief consideration about some side effect, I call, of neonatal screening. I want to start with the USA, because in USA, as I mentioned before, the RASP is an excellent mechanism for programming the screening. And 5 years ago, they included the lysosomal screening in the main program. We know there are the primary program and the secondary program. They moved some diseases, some lysosomal screening diseases, from the secondary program to the primary program. But if you think that in the United States, all the states screen for metabolic disease or for lysosomal disease, is a big mistake. As you can see from the map, only the west part and the east part, in some areas in the middle, they are doing the neonatal screening. But the rest of the United States is really with a very short program of neonatal screening. Just to give you an example, my friend Longo Nicola, he works in Utah. He is consultant in Las Vegas. He go once a month to Las Vegas to see patients. Before, this means that the clinical program and the risk of missing patients in the United States is very high. In Europe, we have a very scarce situation for lysosomal screening. I don't know why, but there are really few attempts to screen in lysosomal disorder, including François here in Belgium. There was a starting program many years ago in Austria, in Vienna, then made by Alpha Bodamer, but he moved to the United States, everything was stopped. And really, it's not popular as for other metabolic screening as we have seen before. This is really a problem that I want to discuss with you later on. What happened in Italy? In Italy, we had really a strong tradition of lysosomal disorders. This is a paper that we published many years ago, 20 now, where we retrospectively made a sort of huge survey in all the centers in our country, and the lysosomal disorders were the most frequent disorders, except for PKU, clearly, much more than urea cycle or the organic aciduria. What happened in the last 10 years? In the last 10 years, we have a national law for at least 40 different metabolic diseases, and including amino acid disorder, organic acid disorders, fatty acid oxidation disorders. And recently, there was a sort of update of the list of diseases, including the muscle-spinal atrophy, some immunodeficiency, and lysosomal disorders. Because at the end, my battle that started many years ago at Sussex, in fact, I started in my region. I luckily live in a quite rich region, and more than 10 years ago, I presented a program to the region, a prevention program, including the lysosomal disorders. And the program was approved, and we started to screen 6 disorders, but only 4 diseases were approved because at that time the therapy was available only for the first 4 disorders. There were no therapy for NIMA-PKB and no therapy for Krabbe. And the program started in 2015, and using a multiplex kit. As you know, you can have 2 options. One option is using the tandem mass spectrometry. The other option is using the fluorimetry microfluid test. We prefer to use the tandem mass, and then later I will explain why. Not because of the kits, basically, but because the possibility to use the tandem mass. It makes the difference. And this is the same machine that you use for the expanding data screening. The only difference is related to the overnight incubation that you need for the enzyme. And this is another important thing, that here you measure the enzyme. You don't measure metabolites. And you measure the low level of enzyme. This means that we spend at least 6 months to create our cutoff, because you need to have a very robust cutoff for the making decision. Despite this huge effort, using only the enzyme assay, as you can see, you have a very high number of recall rate false positive patients. This was one of the first problems that we learned from the lysosomal screening, that if you think to start the neonatal screening as you think to start other metabolic screening using the kits, and you don't have a success. You create only a huge number of false positive, you create all a mess in the clinical work. As you see, the recall rate was, for some disorder like MPS 1, really unbelievable. I never come across in my life a so high number of false positive results. Therefore, the first effort that we made is to find a second-tier test for the lysosomal screening. As you use for, unfortunately, few metabolic disease in the expanded program, in the lysosomal disease, you can really have a benefit from the use of tandem mass, because you can improve the second-tier test using biochemical test and eventually also using genetic test. What I mean with biochemical? We set up a method to develop in dried blood spot the measurement of GAG, glycosaminoglycans, for MPS 1. But this is interesting because you can expand also this second-tier test for all the MPS. And now we are working on that project. We set up a method for measuring the lyso-Gb1 for the Gaucher disease and the lyso-Gb3 for the Fabry disease. I'm wondering that I'm talking about a method that is used in the same dried blood spot. And then that makes really the difference when you want to start the lysosomal disease. Only for one disease, as you see, the Pompe disease, we don't have at the moment a good biochemical method in DBS. We use the tetrasaccharide, but the tetrasaccharide is useful only in the urine and means that you have to recall the patient to get the urine. Another possible approach is, we are working on it, is to use the genetic test searching the most frequent mutation in the dried blood spot. It's not extremely complicated. We have been started 2 years ago, also in parallel with tetrasaccharide. This was the method published for the USA group, and it seems to be good, at least for the Pompe disease. Is used routinely in Taiwan, but as you know, in Taiwan is an island. More or less, they have the same mutation. They have more for Pompe disease, the late onset than the infantile mutation, because it's clearly useful and easy to do when you have a very select population. But we have a population like we are observing now in Italy, where we have a huge number of new immigration from North Africa with a mutation that we don't know exactly. This maybe is a problem. If you look at the literature, it was also to measure the creatinine, and recently at the World Symposium, the World is the lysosomal symposium in United States. This year was in Orlando, and François was there. Somebody, it was just an abstract, they proposed to measure the CPK. Using the routine method, we measure CPK in the lab. But again, this was proposed by Taiwan, where they have the same, more or less the same mutation. I don't think it can be so strong, so robust to using routinely in our population. Therefore, anyway, we have now a good approach in now combining the enzyme to the second-tier test. Now I want to show you the result that we got in a 9-year 9 years of neonatal screening. I started with the Pompe disease. With the Pompe disease, data that we recently published, we see that we screen now more than 240,000 neonates. The birth rate, unfortunately, in Italy is very low. It's less than in Belgium. Well, we had a collapse of the birth rate in the last 2-3 years. And this was a reason because it's very difficult to have a large population studied. But as you can see, we identified 3 patients with infantile Pompe disease. We identified 10 patients with a delayed onset. The number of VUS was quite robust, 9 patients, and the carrier were 4 patients. And only 1 patient was lost to follow-up, was a VUS mutation. This is a problem that we discussed also before. Patients, they are not really sick. How we can manage with the neonatal screening. The recurrence rate was a little bit low, 27 on excellent. But if you look at the result, we are also studying also all the biomarkers to understand if it's possible by neonatal screening to identify the infantile form to the late onset form, to the carrier, to the VUS. Basically, only 2 parameters are useful. The CPK, the tetrasaccharide in the urine. This is a good, excellent marker for the infantile form. And the left ventricular max index that is very prominent in the infantile. This is so-called the cardiac form in comparison with the late onset form. The 3 patients that we diagnosed with infantile form, all patients are alive. As you can see, only 1 patient was CRIM positive. The other 2 patients were CRIM negative. This is another story to discuss. The CRIM negative is considered a very negative patient. It's not true. The CRIM negative needs a very long work before starting the therapy. It's a long time, it's a long work on immunization, and then you can start the therapy. Therefore, it's extremely important to have a rapid diagnosis of this patient. All the patients are now on therapy. All the patients are alive. And just to give you an idea of how it's changing with the therapy, the level I can show you, no, sorry. I want to go back. This one, no. No, sorry. Okay, perfect. Okay. To go back is the red flag. To go back is the one. Okay, perfect. Okay. Okay, just to show you that the tetrasaccharide in infantile form is a good marker for follow the disease. Much better than CPK, there's up and down, and also the left ventricular max is routinely followed in our patient. Then, just to give you an idea, this was the first patient with the CRIM negative. Was very severe form. It was due to a neonatal asphyxia, but despite the so severe form, we were able, with a therapeutic approach, to have a perfect result in terms of muscle. As you can recognize a little bit from the face, this is a Pompe disease, but I never thought in my life a CRIM-negative patient at that age, still alive, I think without the screening is absolutely impossible. Much more complicated is the story of the late onset form, because in the late onset form, you don't have a very good biomarker, except in some patients we observe an increase of CPK, but not in all patients. And the tetrasaccharide was slightly elevated at the beginning in a couple of patients with the late onset, and then obviously totally normalized. Therefore, the follow-up is only a clinical follow-up. It's very also time-consuming, and also it's difficult for the family to understand the severity of the disease. We had the opportunity to have in a couple of families brothers, sisters affected, and in one family, also a Moroccan family also the mother was affected, because therefore was a good model to organize a follow-up of Pompe disease patients. I mean, the 80% of Pompe disease are coming from Morocco. And they notice that they have very high frequency in the North Africa population for this kind of disorders, much more than we thought at the beginning. One was, with infantile form, was from Africa, as you've seen before. Because in the Pompe, the effect is unbelievable. There was a high mortality disease, the infantile form, and despite the cream negative, all the patients are alive. The cream positive is going literally excellent, I mean, absolutely normal at 4 years of age. No symptoms in the muscle at the moment, no symptoms obviously in the heart. Gaucher disease. This is another disorder where, as you can see, the changing to introducing the lyso-Gb1 as secondary test improve dramatically the recall rate of the patient, and we have only 3 false positive after introducing the lyso-Gb1, and a PP value of 94%. Really, you can use, probably you can use also in this disorder, the lyso-Gb1 as a marker. And we use the lyso-Gb1 also to understand the severity of disease. We noticed that the group we put here the level of lyso-Gb1 and the mutation, or the severity of the mutation of the patient. And as you can see well, that when you have only the 409S, the lyso-Gb1 is abnormal, but not so high. When you have severe mutation, the lyso-Gb1 is high already in the first days of life. This is important in terms of follow-up, because in the Gaucher disease, everybody thinks, oh, we don't need to screen the Gaucher disease, because sooner or later we can pick up the patient and we can start the treatment. But it's not really true, because this is our series of patients, and some patients develop hepatosplenomegaly in the first years of life, and also a decrease of the platelets. As nobody takes care of the hepatosplenomegaly, but it's already there. In one patient also, and I will show you later, we observe bone disease already in the first years of life. We pick up also a type 2, type 3 form at birth, really neonatal form. It was confused as a hematological disorder, severe hematologic disorders. I think that nobody without neonatal screening thought there was a Gaucher disease, okay, because the bone marrow was the same that you can see in a very acute lymphodegenerative disorders. The screening was positive. The patient was diagnosed, was treated, and now the patient is 2 years and a half, he is alive. Just the bone. The bone, we think that the bone is a light onset complication of the disorder. This was a patient that we observed because he has never pain, but he has some strange way of walking. We perform with the Gaucher disease. Obviously, we follow the patient every 3 or 6 months according to the age. And we perform magnetic resonance, and was already present in the femoral osteonecrosis of the patient, severe osteonecrosis of the patients. We start to treat the patients, and after 8 months of treatment, the bone is totally normalized, and the child is perfect, is working regularly, no more complication related to the leg. This is something that was surprising us. We recently published this data because the bone disease is considered just a late onset complication. It's not true. We have the natural history of the disease during the neonatal screening. This is an important message I want to give you, because this is the story of the disease. We observed in the past was the disease and the child and the sick children, not the natural history of the disease. And another important is the incidence of disease, at least in the Mediterranean area, is extremely high as a disorder. MPS1, in MPS1, the problem of the second-tier test was enormous. Without the second-tier test, as you can see, the rate, we are more or less, which was the first period until 2018 where the second-tier test was not available, and after. And as you can see, more or less the same amount of neonates screen, and look at the difference in terms of PPV, in terms of false positive, I mean. Because you measure the GAG, as you can measure the GAG as the diagnostic test when you think about mucopolysaccharidosis. It's not the older test, the colorimetric one. It was related to the creatinine. It was extremely imprecise. By tandem mass, you can use the GAG in the plasma, in the urine, and in the ABS. And you have a perfect measurement of the status of the patient. Also for MPS, we have 4 patients now screened. It's interesting that all 4 patients are already bone marrow transplanted before the age of 6 months. The patient, just to give you an idea, is absolutely normal. Look at the difference that we get in terms of bone marrow transplantation. You can drop also of the GAGs when you start the therapy. I mean, but the difference is related to the neurological development of the patient, because it's clear that you start the transplantation as soon as possible, you have normal child. And these are the series of our patients where we have a long follow-up clinic where we are going to measure not only the abdominal ultrasound, but also the cardiac measurement, the audiometry, the ophthalmological, the full X-body ray, and the brain and spine MRI. And another interesting observation that we made that corneal clouding are in some patients present at birth. They don't develop corneal clouding later on, where we thought. No, it's already present in the fetal life. And that was what we observed in all the 4 patients that we identify at the moment. I don't have here a picture, but it was also we reached the national information because one of the patients, the first one, was able to climb a mountain 2,500 meters at the age of 4 years. From the mountains, it was published in the Corriere della Sera, the national newspaper, as a big success of neonatal screening. Fabry disease, Fabry disease. This is one disease very where I have some doubts, I can say. I have some doubts. I tell you so why. Because if you see our data, we have, first of all, quite good PPV. Also, we have the lyso-Gb3 as a second-tier test in all patients. But here the problem is related to the disease itself. Because in the Fabry disease, we have type 1, type 2 disorders. We have a high number of VUS. We have some mutation like the PA143T, where nobody knows exactly is a disease mutation or not. Therefore, it's extremely difficult to manage this patient and to give also correct advices to the family. One important thing in the Fabry disease that we can identify the mother, and the mother is a carrier. And we found 50% of the mothers already with cardiac symptoms. And also we investigate also the other members of the family, and we were able to pick up many other patients that were known about the disease with the age of about 14, 50. One patient had also a slight kidney insufficiency. Because from that point of view, Fabry screening is extremely important as a genetic counseling for the population. As I mentioned before, the lyso-Gb3, we have only one patient with Fabry disease type 1, the so-called the infantile or the late infantile or the childhood form. All the patients were type 2. And in the type 2, the lyso-Gb3 not always is elevated. And this means that you can have a high recall of patients. And also you don't have a good biomarker for the follow-up, because lyso-Gb3 is considered for people who is studying the disease, an excellent biomarker. I am not so fully convinced that it is so good. In female, it's so and so, but also in male, is present, maybe is elevated, but cannot give you advices how to manage the patient with the Fabry disease. We are going on with the Fabry disease because clearly one important is to have experience of disorders. Because, for example, the patient with the type 1 now is presenting some apodrosis. Another important question mark is the timing of starting the therapy. Indeed, obviously, we need a careful observation of the patient. Therefore, this is, in my opinion, the most striking data. They are frequent. If you consider 4 lysosomal disorders, the frequency in our population over 200,000 neonates is 1 every 3,000 patients. If you consider other metabolic diseases we are currently screening, some organic acidurias that are in our program, or the same propionic acidemia, is 1 every 30,000, okay? Including also the mild form, because now it's something to discuss in the future, is the value of the mild form. We are picking up in the neonatal screening more mild form than severe form for organic acidurias or amino acid disorder. Here we have this panel of disorder. For some diseases, we have patients like Gaucher, that in Italy is 1 disease every 12,000 neonates. The PKU, the classical PKU in Italy is 1 every 14,000 neonates. At the moment, Gaucher is, in my area, the most frequent disease, the most frequent metabolic disease. Then we have the Fabry, then we have, including type 1 and type 2, then we have Pompe disease, is 1 every 18,000, and MPS 1 is actually 1 every 45,000. I mean, all very important number in terms of prevention of metabolic disease. Therefore, the conclusion that we have after now 8 years of screening, that the screening is unbelievable as equitable form of diagnosis, because you can offer all the neonates the same approach. It's not doctor or expert dependent. I mean, because the long journey of many of these patients before getting a metabolic and lysosomal disorders, in comparison with the possibility to diagnose all the patients the first days of life, is unbelievable. Then also we are doing to prepare also the family that something can happen. They can manage it much better. We are now working with our psychologists, speaking the psychologists. I don't know if the psychologists are here, but we are following all the patients from the psychological point of view. Overall, for patients like Fabry disease, Gaucher disease, where you have a normal neonate, you don't have symptoms of disorders. And after years, all the mothers and fathers of positive patients were all very satisfied of the neonatal screening. They accept very well this kind of approach. And it's extremely important, the genetic counseling. Fabry is X-linked disorders, because we know the problem. And also is the possibility now of the increase in treatments for lysosomal disorders. Because we started with enzyme replace therapy, now we have moved to the oral therapy. We are ready also to use for some patient bone marrow transplantation, but we know that actually at the NIH there are many genetic therapy programs going on, I mean, for this kind of therapy. But I think that also the other side of the moon, as in medicine. Medicine is never 100%, and I think the problem is relative of the cost. It costs less than spinal muscular atrophy, but the cost. The problem of the VUS, the problem of the carriers, this is the truly problem. We have the same problem also we have the same problem also in other inherited metabolic disease, but here in the lysosoma is an extremely important problem. Also the time-consuming follow-up, and also to convince, this is extremely expensive, because you have to do tests, in patients, they are not suffering. Therefore, you have to take into account also is an extra cost that you can have in these patients. There are also some ethical dilemmas that is not fully solved. Ethical dilemma related, or first of all, that we can create, at least in Italy, we have centers like in my area, we screen for these disorders, but in the rest of Italy, except for another region, we don't have the screening for lysosomal diseases. Therefore, we can create really a puzzling situation for patients, overall for patients severe like Pompe disease, where they die in a region that is 80 kilometers far from my centers. I mean, this is a very truly problem that I hope that we solve with the new law in the next years. But also to develop the screening, I don't think that you can develop screening for lysosomal disorder as well we develop screening for PKU, because it's much more complicated here. You need a good know-how, you need the technology, you need those experience, because otherwise you can have really, as I showed in the one of the first slides, a huge number of the false positive results, and you can create panic in the population. It is a wrong approach of neonatal screening. Therefore, there is still some debate about the screening. The other debate is that I'm working on, why only MPS 1? Why not all the other MPS where you can measure enzymes and also you have a perfect second-tier test to identify patient? Why don't measure metachromatic leukodystrophy? Because there are other diseases you can measure very well in a dried blood spot. This opens a new chapter of the inborn metabolic disease in disorders, I want to underline, that basically are not so easy to diagnose, where the delay of diagnosis is a serious damage for the patient, because you cannot approach in the same way with the same therapy if you diagnose the patient in the first days of life. And last but not least, we can understand the natural history of the disease. The natural history of the disease for many metabolic diseases are totally unknown. One of the big success of neonatal screening is really to understand not only for lysosomal disorder, but for all the diseases, to understand the history, the natural history of these patients, and also to find the time to start the correct treatment. Again, I want to invite me for this meeting, and I hope that in Belgium, I hope that France go on with the screening of lysosomal disorders, because in my opinion, after 8 years, is an extremely important screen, not for us, not as doctors, but overall for the patients. Thank you very much for your attention.
Thank you very much for this very nice talk. Unfortunately, we are a bit late, so maybe one quick question.
Who wants to ask a question? No one? So the only thing, well, I'm going to ask the question. Thank you, Alberto, for this nice presentation. So the first thing I wanted to ask, well, the gags that you perform with tandem MS, what methods do you use?
We use a method that we published recently, but it's more or less the method published in the literature, where we measure in the dried blood spot using the retention times, all the heparan, dermatan, keratan, and chondroitin sulfate. The most important thing to do is to have a good correlation line. I mean, because this is a process where you have to set up for every time you have to measure the gag. You need a very well done curve. I mean, otherwise you can have not reliable results. Because this is the only important thing to do, to organize a standard curve with different amount of single gag to be sure that the result is reliable. But it's not with the tandem mass, is really something to perform. So, you know, the Japanese group tried to screen patients starting just from gag instead of to using the enzyme. I don't think I think you need both at the moment. I mean, I think you need both to be sure about the result, because you can also in the MPS the truly problem is the huge number of pseudodeficiency. Is a pseudodeficiency a possible disorder or not? But we decide don't follow the pseudodeficiency because it's too large the amount of work to do.
Okay, thank you. Thank you.
Thank you.
Now I'm glad to introduce Professor François Boomer. Professor François Boomer is a pharmacist and a biochemical chemistry specialist by training. He is head of the newborn screening center and biochemical genetics laboratory in University Hospital of Liège. He is an expert in newborn screening and has been at the forefront of the development of newborn screening for sickle cell disease by MSMS. And more recently, he was deeply involved in the implementation of newborn screening for SMA. Professor François Boomer, the floor is yours.
Thank you for giving me the opportunity to present here our new project named Baby Detect. It's a project based on newborn, next generation newborn screening. Well, just a brief overview on what is newborn screening. Just a reminder, so newborn screening is a public health action to identify and treat at birth severe congenital defects. It started in the 60s by the Guthrie test to screen for phenylketonuria, and in 68 the WHO organization defined with Younger and Wilson criteria to include disorders into newborn screening program. Among these criteria, the disorders needs to be a public health problem. It needs to be accepted by population. The disease needs to be, the physiopathology of the disease needs to be well understood, and the screening needs to be done at a pre-symptomatic stage, and you need to have a therapeutic protocol with an efficient treatment. There's also a need to have a validated and reliable test. It needs to be cost-effective and sustainable. So that's how newborn screening works. You all know that. So after birth, all neonates are blood. A few drops of blood are collected on a filter paper and then sent to a centralized newborn screening labs. In Belgium, we have two screening programs. I'm working in the Wallonia part, the French part. So we are currently screening for 19 disorders, including inborn errors of metabolism, endocrine disorders, and during the last 2 years, we introduced the screening for SMA and also for sickle cell disorders. But if we compare, so we are currently screening for 19 disorders, but if we compare with the RUSP list, the RUSP is the Recommended Uniform Screening Panel, which is a list driven by federal government in the US. They recommend the screening for 37 primary conditions and for 26 secondary conditions. So we have here 63 disorders, and in our area, we are screening for 19. So why not trying to do best? Why not trying to do more? Indeed, many genetic diseases could be detected and treated at birth, but they are not because no biomarker currently exists. So I will show you the video from a patient from Congo. He arrives in Belgium when he was aged from 10 years. He has a severe motor weakness since birth, and he was diagnosed in Congo being affected by Duchenne dystrophy, but we'll see it's not Duchenne dystrophy. He was suspected to have a spinal muscular atrophy, but it's neither spinal SMA. So so you can see the severe motor weakness since birth, so he cannot walk alone. He needs to be in a wheelchair since birth. So and after several months of workup, final diagnosis could be done. It's a congenital myasthenia syndrome with a mutation of DOX7 gene. It's a protein in the synaptic region, and these disorders can be treated with salbutamol. Salbutamol is a beta-2 mimetic, which is currently used in patients with asthma. It's commercialized under the name of Ventolin. Its cost is about €7 per month. And here you have the same patient after 2 days of treatment with salbutamol. So he can walk alone, so it was a few years ago, and nowadays he's still under treatment, and he can run alone. So with a very low, so he spent several years of life into a wheelchair, and if he could have been identified at birth, so we would have spared this huge and severe medical cost for the society for this kind of patient. Making a brief review of all these, some disorders that could be already treatable at birth, we can assess the theoretical incidence of several disorders, including genetic central hypothyroidism. In Wallonia, we could have 3 patients per year. Brown-Violeta van Laar, which are disorders of vitamin B2. So we have about at least a few patients also per year. In total, if you add all these disorders, we can identify at least 15 new patients per year, and all these disorders are currently treatable, but are not identified at birth yet. So for most of these disorders, all patients have a very long diagnostic odyssey. We can also make the same review for new disorders that could be included in future clinical trials, like for Dravet syndrome, Angelman, Rett syndrome. So we can, including all these new disorders, we could add about 20 new patients per year in Wallonia. So then, based on that, came the idea of Baby Detect, which is the introduction of next generation sequencing into newborn screening as first tier test, not as a second tier test, but as a first line screening method. So we aim to implement the NGS for newborn screening, and we designed a website to inform future parents about the project, and to ask them if they want to participate in the study. So we have a website named Baby Detect, which describe all the project with all the disorders, with all the genes included into the. I will show you later on which genes are considered, but which genes are included into the project. You have flyers, we have videos where patients, future parents can be informed on the project. So information and consent of parents. The information is first done by gynecologists during the end of pregnancy, because we try to inform parents on the project before birth, because if we wait after birth, so there's a huge emotional situation, so they are not very well attentive or receptive to the information. So we try to inform them before birth through the gynecological consultation. And when after birth, the nurses in the maternity approaches the parents, and they ask them if they want to participate to the study, and we collect informed consent either digitally or on paper. So this is the pathway of consent collection. we implemented a platform to collect electronic consent. So nurses approach the parents with a tablet, and the parents are informed on the project. They say if they want to participate or not. They have to sign on the tablet, and they have to consent on 3 different points. If they want to participate to the study, if they agree that the medical information based on the study could be used in the future for future medical consultation, and they also have to agree if we could use in the future their genetic material on an anonymous manner for future clinical research project. So this is the platform, the website where we collect informed consent from the parents, so the nurses connect to this platform, and we are currently consenting and screening newborns since last September 2022, and we have implemented the project into currently only 1 maternity in Liège area, where we have about 2,000 births per year. So since September, we have collected 1,400 consent, and we have 147 refusals, which is a very unexpected high level of acceptability of about 92%. So what are the molecular criteria to include a gene or a disorder into the program? So the mandatory criteria to include a disease or gene is that the disease has to start at the pediatric age, before the age of 5 years. It needs to be severe with a significant disability, if not treated. It needs to be, an approved treatment needs to be available, or a clinical trial, at least phase 3. There needs to be a good technical approach, NGS, but not only NGS. For example, SMA is not really easily identifiable by NGS. There need to be very clear pathogenic mutation and highly penetrant mutation. Here we have developed a custom target NGS panel, which includes currently 361 genes for 126 treatable disorders. And this panel is reviewed on a periodic manner. Every 6 months, we have a meeting with 11 clinicians from 11 experts field, and we review new genes, new disorders that could be included into the panel because of new treatments, new knowledge on these disorders. So including the panel, we have the 119 genes from the metabolic diseases. We have 49 genes from endocrino, 47 from neuro, KID, human deficiency 44, hematological gene 43, gastro gene 23, nephro gene 18, cardio 17, and onco-ophthalmological, which is RB1 gene, 1 gene. So you may ask me, why do you use a custom target panel? Initially, it's not exome sequencing or genome sequencing. Initially, it's mainly based on financial aspects. It was much more. It was less expensive to use a target panel than exome sequencing. That's the reason why we developed a target panel. And additionally, the other advantage is that it could improve the coverage of some regions, some genes, compared to exome sequencing. The reason why we also included metabolic genes is that it was a publication in Nature Medicine a few years ago which compared NGS with mass spectrometry, and it's currently well known that the biochemical approach is much more sensitive than NGS approach for inborn errors of metabolism screening. But we included this gene because we collect the card from the Baby Detect project in parallel with the Guthrie card for the classical newborn screening. So we can compare the results from biochemical assays with the NGS results. So we could this way to improve our genomic knowledge on these genes. So that in the future we aim to make genotype-phenotype correlations for these metabolic genes. So here's the Baby Detect workflow. The blood from neonates is collected on the same cards and on the same kind of cards that for a classical Guthrie card. It's named the gold card. It's a second card, which is the same one as the normal one, but it's gold. And you have on the right side of the figure on the right side, it's a workflow for the project. So we spot three spots of 3 millimeters diameter into tubes, and we extract DNA. Currently, extraction is done manually. This extraction takes about 1 to 2 days. The library prep, it's a preparation of a library before sequencing, takes 2 days. Sequencing on sequencing devices takes 1 day. Demultiplexing takes 2 days. Demultiplexing is as we sequence several patients all together, we can identify patients by attributing them molecular tags. So we can identify the sequence specifically for each patient. So we need to bioinformatically, after sequencing, to demultiplex all these patients to assign all the fragments or the sequence to a specific patient. And these steps takes 2 days currently. And then interpretation of result takes 1 day. So in total, the workflow takes about 10 days. So our aim is to have a turnaround time between 1 and 2 weeks in the future. So DNA extraction is currently done by QIAGEN columns. It's a manual steps. I will not enter into details, but we are trying to validate an automatic liquid handling system for automation to improve our throughput. We use Twist Bioscience technologies to prepare libraries. We'll not enter into these technical details, but we have validated these technologies on our panel. So that's what the different steps we implemented in the beginning of the project. So we assessed the quality of our libraries before sequencing. That took time, but currently we are not doing that anymore because we know that's the reliability of the process as well. So we try to save time and save workload into the process to improve the throughput. And sequencing is done on Illumina devices, either on NextSeq or NovaSeq systems. And we have a custom panel of 1.6 megabase. After sequencing, we assess the quality of our sequences. On a multi-QC report, we assess the coverage for all our patients, the coverage for all our variants identified in all patients, and we have fixed a threshold of acceptability for all these variants. We also identify about between 2,000 and 3,000 of variants per patient. I will show you how we interpret them. And we also have in the right figure, we also have the coverage by chromosome, and on the right side of the figure, you can distinguish male and female patients with a coverage related to the X chromosome. So interpretation of variants, that's a tricky part of the project. We use ALISA Interpret interface. It's commercialized by Agilent, and we have designed a classification tree to filter variants because we identify 3,000 reliable variants per patient. We cannot spend time to review all these variants one by one for the several hundreds of patients we have. So we need to filter them and to have finally the less variance possible to validate or not a patient. We currently report only class 4 and class 5 variants by the class 4 and class 5 by the ICMG classification, and class 3 variants, the VUS, are currently disregarded. We could only consider class 3 variants for disorders where we have a second-tier test available, second-tier biochemical assay test available. And also currently CNV's copy number variation identification is not available. It's under development, but currently it's not available. So this is a kind of screenshot of ALISA interpret sheet. So one line is one patient, and per patient you have 7,000 of variants, from whose about 3,000 are considered as relevant, reliable, and we cannot spend for all these patients a long time to assess a variant. So we need, if we want to, that's a screening method. So we need to have a very good throughput, and we cannot have a lot of variants to be reviewed per patient. And so what's it? So we have here the flow, the classification tree, and we try to get to have the less variance per patient to review. And if we have one variance to be positive, if we have patients to be positive patients, as I said, it's a screening method. All patients need to be confirmed by an alternative method on an independent sample in a diagnostic genetic lab. So I want to emphasize that remains a screening method. That's not a diagnostic method. We cannot rely on these screening results to assign a disease to a patient. It's a suspicion of disorders, and it needs to be confirmed by an independent method on an independent sample. The method was also validated using different kind of samples. We have positive samples on filter paper. We also use the GIAP samples. I will explain what is a GIAP samples. We have negative samples. We also collected blood from 30 adult normal patients, both on DNA and on filter paper, and so we can compare the results generated by our sequencing between collection on filter paper and a normal extraction on whole blood. The GIAP samples, GIAP is the acronym for genome in a bottle. It's a commercial DNA you can purchase, and for which all the mutations in this DNA are very well described by several genome sequencing methods. So you can really trust in the variants in these GIAP samples, and then we compare our the results generated by sequencing methods, our sequencing method for these samples, to what is expected in the reference method, and so we can calculate the PPV and the sensitivity for all these for this GIAP sample. And so we have a precision and sensitivity. We calculate precision and sensitivity both on the two sequencing machines we use, and NextSeq and NovaSeq, which is for SNPs, for variants. We have a precision above 90% on both NovaSeq and NextSeq, and we compared it to the whole exome sequencing validation data we get from our diagnostic lab, and we get more or less the same precision and sensitivity that the whole exome sequencing method. So we were rather satisfied with that. I guess you wanted to ask me some information about the costs for patients. So currently, we have developed three three perspectives based on the finance we have. Currently, we have the finance, I will show you later, the following slides, the finance to screen between 5,000 to 6,000 patients in 3 years. This is the first line. And based on that, if we consider reagents, equipment, human resources, and other rentals, the cost per patient is about 365 euros. If we increase the number of neonates we screen up to 19,000, we can reduce the cost to 262 samples, and if we can also increase, we can be less than 250 euros per patient. This cost, note that this cost includes also human resources, which has an important part of the cost. It seems very expensive, but we can consider it on a positive way. If we can make a comparison on what we are paid currently for the screening of 19 disorders. For 19 disorders in the classical biochemical screening in Wallonia, we are paid about 40 euros. So that's about 2 euros per disorders. Here we are screening 120 disorders. If you multiply per 2, so we have more or less the same cost. So it's not, if you consider the cost in terms of diseases, it's not more costly than classical biochemical screening. Well, how is the project financed currently? So we have money from the underspend from the newborn screening SMA project, which was achieved 2 years ago. We have found prize from the Leon Frederick Foundation. It's a foundation in the University of Liège. We have investigator initial trial from pharmaceutical industry, Orcat, Takeda, and Sanofi. We have also been sponsored by Zentech, and we have also pending requests for the pharmaceutical companies. So we have now screening in only one maternity, but we aim the perspective is to propose a screening to all our maternity network. So before of that, we need to implement automation of our workflow. Currently, everything is done manually. That's for a few samples, that's okay, but if we consider several hundreds of samples, you need to automatize your process. So this automation is mandatory to extend the project to new maternity wards. I also presented you that we were using a custom target panel, but we consider since the cost of the exome sequencing is becoming lower and lower, we are considering now the implementation of whole exome sequencing that would make things more easier for us to implement new future genes into our panel, because the whole exome sequencing already includes these genes, but you can disregard them if you are not interested with them. And we also will aim to implement systematic and quantitative criteria to include new genes, because currently it's based on discussion with specific experts, but it can be discussed. So we want to have a more pragmatic approach to include future new disorders. Well, that's it. I thank all the team who was working on the project.
Thank you very much for this very nice talk. Any questions? Maybe you can start. What is your TAT now?
I don't say that currently. It's long now. In the consent, we say parents sign that if they have no contact within 3 months after sampling, that's the same that for classical newborn screening. No good, no news, no good news. So currently we want to be below 3 months. but we aim to improve up to 1 to 2 weeks in the future, yes. But we need automation, we need to implement all this new workflow.
Very nice talk, and thank you.
Thanks.
Did you have any findings?
Any?
Any findings? New findings?
Yes, but we do not communicate on findings yet.
It's a secret. Okay.
Yeah, thank you for the very nice presentation. I was wondering, I could see in your gene list that several ones had pseudogenes as well.
Yes, yes, I know.
How do you tackle that?
There are in the panel for SMA, we included SMA, SMN1 and SMN2 genes, but I'm pretty sure that will not work. So that's the reason why it's necessary to keep the qPCR or the digital PCR approach nowadays, or implement new approaches, for example, nanopore sequencing. But for SMA, for some genes, we will need to keep alternative approaches. It's the same for Angelman, which is probably one of the next diseases that will be considered by screening programs. We will not be able to screen Angelman with Illumina technologies. We will need either qPCR after methylation sensitive or nanopore technologies.
Yeah, and for instance, cerebrolipofuscinosa type 3, yeah. I think 60 to 70% of the disease alleles is a 16 kb deletion. I don't know whether this is also, is it in your list? Or do you,
which one?
CLN3.
I don't think so. It's already in, it's under CLN are under consideration, but not yet, I think.
Okay, thank you.
Thanks.
Thank you.
We will now start with our free communications. I'm happy to say that we have received a lot of different subjects. So I want to start with Sylvie de Vos, which is going to tell us something more about a multiplex analysis for lysosomal storage disorders.
Thank you for this invitation to be able to present some data on the validation that we did for the measuring lysosomal enzymes on dried blood spots and for neonatal screening, but also for diagnostic purposes. Yeah, as you probably well know, lysosomal storage disorder, or LSDs, are so rare metabolic disorders caused by enzyme deficiencies and causes lysosomal malfunctioning. There are around 50 LSDs known with all different clinical outcomes. And here is a slide just to present that if large molecules, like here dermatan sulfate, cannot be correctly degraded, it gets stuck in the lysosome. Lysosomal cells, the cells are damaged in the end. So a lot of enzymes are involved in the degradation of these large molecules. And here, for example, this pink bullet representing the enzyme, which, if it's not working, causes MPS 1, MPS 2 first, and then MPS 1, MPS 6, then the Tay-Sachs disease, and also MPS 7. So all these enzymes have a different function in the degradation of this. So it's very important. If we can look at all the activity of the enzymes, it can give clear picture of the diagnostics. Unfortunately, we cannot do this for all the enzymes yet, but we try as much as possible to include a lot of enzymes in the panel. And as Professor Borlini already mentioned, there are actually two platforms to measure this enzyme activity. One is the LCMS and the other is the fluometry. We also have chosen for the LCMS method because it has some, for us, some benefits that you can multiplex enzymes, and also in the end maybe to include in the same analysis biomarkers like the lyso-Gb1, lyso-Gb3, and maybe future other biomarkers. And the method is based on the work that was done already in 2000 by Gamoles, who saw that if you have a dry blood spot and you solve it in a suitable buffer, the enzyme activity remains active, and you can provide some synthetic substrate to this enzyme, have it incubated, and then you can, if the enzyme is still functioning, you can measure a product on the LCMS. When the enzyme is not functional anymore, you don't see this product peak, so that's to distinguish patients. So here is the list of all the enzymes that we now have in a scope with a validated and accredited method. And on top, we tried as much as possible to use kits because of the new regulations on IVD, but not for all the enzymes it's possible. There are no kits yet, but the first 6, so here is the Gaucher, Pompe, Fabry, MPS1, the Niemann-Pick and Krabbe are in a kit that we have from Perkin Elmer. And then the other 10, so MPS2, 3A, B, and C, 4A and B, 6, 7, TPP1 and lysosomal acid lipase are in an in-house method, and we try to multiplex as much as possible. Just a few results of our validation. We have here the chromatograms of all the enzymes, and for example, I will just, so for each of the enzymes you see 2 peaks. One in front is the product peak, and then the internal standard, which is for all the peaks available. And if there's a healthy, normal working enzyme, you have a large peak. I don't now have a picture of when it's not working, but then the peak is very much lower compared to the internal standard peak. All the results were linear. We used the product to assess linearity, but we cannot do this for all the enzymes because we don't have the product for all the enzymes, because it needs to be generated during the assay. So we don't have a curve during all the work, but so the analysis is semi-quantitative. Some results on the variation. So for all the 16 enzymes, you have the means and the standard deviation, and also the variation, which is all reasonable for semi-quantitative analysis. In the literature, there's not much data yet on reference ranges for the enzyme activity. So we did a large study on different categories, so male, female, but also the age-related reference intervals. And what we noticed, if we did the analysis already for the neo-LSD kit, not yet for the in-house, we're working on that still. But if you see that the enzyme activity in the neonate is always much higher than in the older population. I think it's not for all the enzymes, but for some it's really obvious. We tested our method on some patients. We didn't have patients' material for all the assay, for all the enzymes. But the ones we had are showing that the enzyme activity is lower than the reference range in this category. And we also use the CDC controls, which are specially designed as quality controls for the LSD enzymes. So the CDCA is a card with where there is only leukocyte reduced blood, so there is no enzyme activity in these cards. We could see that there is only for GUSP, so for MPS 7, that there was still some activity, maybe in the cells, but we have a patient for MPS 7 which is showing very good. We could pick it up with the assay itself. So we can conclude that we have an accurate method that could confirm known LSD patients. We can pick up patients. It has short sample preparation and runtime. For example, this Neo-LSD kit, it only on the instrument, it's only half a minute for an analysis, so it's easily combined even with the methods for the acylcarnitines and the amino acids. So it can be in the afternoon and then the rest during the night. It's really we thought it possible. Then we were also able to establish the specific ranges for the assay. So consider the analysis as suitable for screening and also for diagnosis of at-risk patients. I want to give a special thanks to one of our MLTs, Karen Bermijn, who did all the work, all the reference ranges study. And if you have any questions for this, you can always contact Laurence Roses, who is a clinical biologist that is responsible for this test in the USA lab. Thank you.
Questions? I will not throw, I promise. No? Yeah, then I think we'll just go further for.
Let's move on with Dr. Bram de Croo. He will explain us a very interesting case about HMG-CoA synthase deficiency.
Thank you. It was a normal day in the University Hospital of Leuven when suddenly, again, a girl of 2 years old presented with increasing somnolence. She had a gastroenteritis for about 2 days and a pollen tissue intake for about 24 hours. Clinical examination showed an almost unresponsive infant with hepatomegaly. Laboratory tests showed a profound hypoglycemia with lowered sodium, increased ALT, AST, increased CKs with lowered TSH, IGF-1, and sharply increased cortisol levels. But what was most strikingly is that this kid had low to absent ketones in her urine. This, in combination with the profound hypoglycemia, was the beginning of a very interesting case. My name is Bram de Croo, and I'm going to present to you a case of HMG-CS2 deficiency and tell you a little bit more about the importance of measuring ketones in the case of hypoglycemia. But let me tell you first something more about the physiology. So in the normal fasting state, you break down glycogen to maintain your glucose level at a quite steady level. When the fasting is prolonged, you start to break down the adipose tissue, and the fatty acids and glycerol are released. Fatty acids are then transformed into ketones, which can serve as an alternative fuel for extrahepatic organs such as the brain. But in our case, the first and rate-limiting step of the ketogenesis is impaired. Therefore, fatty acids and decarboxylic acids start to accumulate, and the alternative fuel that was available in prolonged fasting for extrahepatic organs, such as the brain, is no longer available. These cases then typically present with hyperketotic hyperglycemia, a metabolic acidosis, and present with vomiting, hepatomegaly, somnolence, which can go into a life-threatening coma. In the blood, we find increased free fatty acids with relatively low ketones, and in the urine, we find increased C2 over C0 acyl carnitines, as well as increased decarboxylic acids. Furthermore, we find relatively low ketones, and since 2015, we can find some biomarkers. But what is very interesting, also with the context of the presentations that have been given, is that in between those episodes, we can find no clinical or biochemical evidence of this disease. The onset of symptoms is typically below the age of 2, and as the age increases, the episodes tend to decrease. Patients normally have a normal adult life, but once a patient has had a case, of course, the parents and the child itself knows what to do to prevent it. So in the case of our little girl, also she had increased decarboxylic acid, sharply increased C2 and C4 acyl carnitines in combination with low free carnitine, and we did find the biomarkers suggested by Pitt et al. In 2015. But let me tell you something more about biomarkers in very rare diseases. So a diagnostic biomarker is a biological characteristic that can be objectively measured and evaluated as a signal of normal biological and pathological processes. And it thus has the potential to improve diagnosis, to predict disease manifestation, or to monitor responses to therapeutic intervention. Since 1979, when the first case was described, for 18 years there was no diagnostic biomarker. Since 2015, we have those biomarkers. Adipic acids and 4-HMP above a certain level are proposed as diagnostic biomarkers in this case. Also, we can find in those contexts of ketotic hypoglycemia some other metabolites that we normally can't find in patients, or not in high levels. And when we then look back at the criteria, we can indeed evaluate these metabolites by GCMS. It's a part of the pathological process. It's probably produced in the context of accumulation of metabolites upstream of the defect, and it has the potential to confirm the diagnosis of HMG-CSF2 deficiency. But is this latter really true? Has this the potential to improve diagnosis? First, let me look at this particular case in this particular context. The true kingmaker in the diagnostic evaluation was the finding of low ketones in combination with hypoglycemia. This set in motion the entire diagnostic workup for the metabolic analysis. If low ketones were not determined, nobody would have thought to go even furthermore, biomarkers in the diagnostic context in very rare diseases have some challenges. This disease is only known in 30 to 40 people worldwide, and so knowing a biomarker as a clinician in this context is not always evident. If we then look at all the articles of case reports that have been published after the biomarkers were already known in 2015, you can see that only 3 of the 22 patients that have been discovered since then have been found thanks to the finding of these biomarkers. Most of the cases were defined thanks to genetic and knowledge of the diagnostic pathway, knowledge of the analysis of organic acids. Those were the kingmakers in the diagnostic workup. Also, can we really determine diagnostic accuracy in such rare diseases? If we now look at the positivity of these markers suggested by Pitt et al. In 2015, you can he stated that it has a positive predictive value of about 80%. He made this conclusion on the fact that in his cohort of organic acids analysis, which was an impressive 8,000 samples, he had 8 samples of HMG-CSF2 deficiency. But of course, as you all know, and as also have been shown in the presentation before, positive predictive value is very dependent on the incidence of a disease. If we then pure hypothetically change these values, for example, this one case that we found in Flanders, and then calculate for the amount of births in 2 years, you can only find a positive predictive value of 2%. And this child came to a university hospital. Within 2 days, she had the analysis of the organic acids, which then led to the diagnosis. If this child had presented to a peripheral hospital and was immediately treated and no samples were taken at that moment, the diagnosis would probably never have come. So, in the end, if I can give some take-home conclusions, the biomarker led to the biochemical diagnosis of HMG-CSF2 deficiency, but biomarkers in rare diseases are challenging. Therefore, an adequate diagnostic workup and knowledge of the pathophysiology stays of the utmost importance. Therefore, please determine ketones in hypoglycemia.
Thank you very much. Any question? I may have one.
Yeah.
About this compound 4-hydroxy-6-methylpyrrone.
Yeah.
And the other friends described by James Pitt.
Yeah.
Was it increased outside the crisis?
No, so indeed after some of the metabolites decrease already after, if I'm not mistaken, 48 to 72 hours, and some other cases as well. I don't know by heart anymore for our case, but so outside the case, it's perfectly possible that you don't find these metabolites anymore.
Thank you.
Other question?
So it was not really a question, but just a comment.
Okay, thanks.
Because we also had actually a new case of this diagnosis 1 year ago also in Belgium. So that means that it's probably not as rare as we think it was, but probably that it has been diagnosed very early. So
no, indeed, there are probably three reasons why it's heavily underdiagnosed. First of all, if a child comes to the clinics and is immediately treated with glucose and intravenous fluids, the child becomes better, and then if it becomes older and never has a sharp or a vast fasting state anymore, then probably will never have any more problems. Second of all, I forgot there were multiples, but I can't. Also, if there are also people who never present with the disease, although they have the mutation, again in certain contexts. And third of all, again, to change my mind, there was a third reason that I was expecting those questions. Yes, there was certainly an underestimation.
But just it can be really life-threatening, as our patient was in a pediatric intensive care unit and needed hemofiltration because she had very, very severe persistent acidosis with severe hypoglycemia. And so it was probably also one of the reasons why we didn't diagnose them before, probably because some of them just died at the IQ.
Yeah, that would be the third reason. Some of them who didn't get diagnosis would have died before. Thanks.
Thank you.
And now, as last speaker before the lunch, it's François Xavier, and he will tell also something more about the cases which they have found.
Good morning, everyone. I'm Dr. Van Vief. I'm a pediatric fellow in a pediatric unit. In pediatric intensive care unit in Jolimont Hospital. Today, I would like to thank the Symposium committee for giving me the opportunity to let me introduce you to a case report of a new diagnosis of sodium-dependent multivitamin transporter defect, which has with an unusual cardiac presentation. I have no conflict of interest. So A is a 5-month-old girl presenting with 2 close episodes of altered general state, feeding difficulties, and a fast severe hypotension in the course of an infectious disease. She had no personal specific history and a normal psychomotor development, but we observed a microcephaly and a failure to thrive from the age of 4 months. The familial history was marked by consanguinity and a death for a brother at the age of 8 months of life from unexplained multisystemic decompensation, also in the course of an infection disease. Both episodes were marked by lactic severe acidosis, and initial cardiac assessment showed a cardiogenic shock with increased troponin and proBNP and with a severe altered left ventricular function, with a ventricular expression fraction of 31% for the first time and 17% for the second time, for a normal value above more than 60%. Importantly, between the two episodes, the cardiac function was totally normal, but after the second one, the patient kept some deficiency and she needed some chronic treatment, cardiac therapy. Both of the time, the patient was hospitalized in pediatric intensive care unit for several weeks, and she developed persistent diarrhea, feeding difficulties, resulting in absolute no weight gain during the hospitalization, and she also developed in the meantime a neurodevelopmental delay. On further investigation, we noticed a severe hypogammaglobulinemia with thrombopenia and transient hypocalcemia and hypophosphatemia. On infectious assessment, on the first episode, there was nothing specific, but on the second one, we highlighted an acute COVID-19 infection. Concerning the neurologic assessment, the EEG and the CT scan were totally normal, but the MRI showed a thin corpus callosum. And on further metabolic assessment, we showed a moderate increase of long-chain acylcarnitine, a low free carnitine value, and a slight increase of C3. According to those results, specific in vivo study of mitochondrial beta oxidation on leukocyte has been performed, but it was totally normal. Interestingly, we found a persistent increase of urinary 3-hydroxyisovaleroic acid, motivating the control of biotinidase activity because we thought about biotinidase deficiency, but it was normal both of the time. And in this case, we thought about the sodium-dependent multivitamin transporter defect. Considering those two severe life-threatening events and a specific metabolic assessment, we asked for rapid whole exome sequencing in trio, and we had the result in 1 month, and it showed a probably pathogenic missense mutation on the gene SLC5A6. Quickly for the treatment, for both episodes, the baby girl was admitted in pediatric intensive care unit for respiratory and inotropic support. And she, because of the suspicion of metabolic disease, she received intravenous perfusion of saline and high level of glucose, up to 10 milligrams kilo per minute. At the first decompensation, we also treated her with L-carnitine because of the first value of the plasmatic acylcarnitines. And at the second decompensation, we added a multivitamin cocktail therapy with B2, biotin, and B12, and B1 also. And as soon as we received the specific results of the organic urinary acid with 3-hydroxyisovaleroic acid increase, we increased the dose of biotin to 10 milligrams a day. And then when we had the results of the genetic results, we also added pantothenic acid. For other treatments, she has been treated with intravenous immunoglobulin, and she was supplemented in calcium and phosphate. And she also needed chronic cardiac therapy up to 4 treatments. With these treatments, she showed, and she still shows, an impressive neurodevelopmental improvement, gradual enteral feeding, and no more diarrhea. And since then, she presented no more metabolic decompensation, and her value of IgA and IgM has increased, for sure IgG2 because we treated her, and her phosphocalcic regulation was totally normalized. The cardiac function is better today, and for now, she still needs only 1 treatment. So the mutation we identified in the SLC5A6 gene is an important one because this gene encodes for a sodium-dependent multivitamin transporter. This transporter is transmembrane protein, which allows the intestinal absorption of water-soluble vitamins, but it also plays a role for the transport of those vitamins in specific tissues, including cardiac tissues and cerebral tissues, and it allows the intracellular intake of those vitamins. More importantly, this is a specific transporter for biotin, pantothenic acid, and alpha-lipoic acid. These vitamins have a broad role on specific metabolic pathways. For example, biotin is an essential micronutrient involved in various metabolic pathways as a cofactor for carboxylase. For example, it's involved in glycolysis, as you can see on the right part with the green color, and it's involved at the level of pyruvate carboxylase. And on amino acid metabolism, it is important as cofactor for the methylcrotonyl-CoA carboxylase. And this carboxylase is implicated in a leucine breakdown. In case of biotin deficiency, you may find, as we found, 3-hydroxyisovaleric acid because this enzyme doesn't have a specific cofactor, the biotin. On blue, you can find the other vitamin, the pantothenic acid, and on red, the lipoate acid, and they both play an important role as cofactor in the degradation pathway of some specific amino acid, including leucine, isoleucine, and valine, but they also play a role in glucose homeostasis, cycle Krebs, and in fatty acid oxidation, which is 3 important pathways for cellular energy function. So currently, what do we know about this disease? This is an autosomal recessive disease first described by Subramanian and his team in 2017, so it's quite recent. There are for now 12 cases reported worldwide, and by the lack of intestinal absorption and especially the lack of intracellular intake of the specific vitamin, this disorder is mimicking biotin-indused defect. So for the next part of the slide, the symptoms of our patient are in bold. Among the 12 patients reported, the symptoms are mostly neurologic or gastrointestinal with neurodevelopmental delay or regression, and microcephaly and brain anomalies with cerebral atrophy or thin corpus callosum for the neurologic part, and cyclic vomiting, chronic diarrhea, feeling difficulties, and failure to thrive for the gastrointestinal ones. Metabolic decompensation can happen during infection of after surgery, and immunodeficiency and osteopenia may also occur. These 4 groups of symptoms describe the first group of patients in the literature with younger age at diagnosis. But interestingly, on the other hand, recently, Orling and his team described another phenotype of patient with this mutation. And this phenotype is restricted to a specific motor neuropathy with no systemic symptoms, but they are diagnosed later in life. Concerning the metabolic assessment, 2 other groups describe also a patient with severe metabolic acidosis and specific persistent elevated urinary 3-hydroxyvaleric acid and elevated plasma C3 carnitine. And one of the important points for today is the treatment. The 3-vitaminic replacement therapy tried in literature with biotin and pantothenic acid and sometimes lipoate leads to a good impact on patients, with an impact on growth and neurodevelopmental catch-up, with impact on resolution of the gastrointestinal symptoms, and with the absence of metabolic decompensation relapse. But there are still some unanswered questions about follow-up and treatment. Every study described a specific regimen treatment based on the Subramanian regimen treatment and on the regimen we use in biotin-indused deficiency, but there is no consensus for now. And it seems that if the treatment is started later, for example, after a neurologic regression, the impact on the patient could be less important. In our case, the replacement therapy was started within 2 months after the diagnosis, and it shows a really impressive symptoms improvement. The last point concerns cardiac involvement. Our patient showed up with a specific cardiogenic dysfunction and with a cardiogenic shock. And this cardiologic dysfunction persists after treatment and after stabilization. And among the other patients described in literature with this mutation, there were only 2 other patients with cardiac symptoms, but the clinical presentation is not really the same. One patient had a right heart failure, but it was after resuscitation, and the other one has a chronic dilated right heart disease. So SMVT is a recently described disease with a quite specific symptomatology mimicking the biotin-indused deficiency. And we describe today the first case with specific cardiogenic shock. The metabolic assessment is specific and can help for diagnosis, and we think that rapid genetic testing should be launched as soon as possible. But in case of high diagnostic suspicion, we think that rapid therapeutic challenge with the vitamin supplementation could be really useful and could have a good impact on patients. Thank you very much. I'll be happy to take your question.
I was just wondering, the 3-hydroxy is of allyl carnitine. Is that also elevated or not?
I don't understand which one.
The carnitine version of your 3-hydroxy isovaleric acid.
I don't think so, but I'm not sure of the answer.
Okay. Yeah, it must be. Yeah? It wasn't? It wasn't at the beginning. Oh, okay. It was not in C5OH. Yeah? It wasn't at the beginning. It wasn't elevated. Should be. Okay, thank you. And I think we can end.
We end, yeah, it doesn't work. So now we're going for the lunch. So the morning session is over. So the lunch is until 2 o'clock and it is in the Marble Hall. But just all the people that want to vote for the next presidency, they are expected to come back. And it is not, well, 1/2 hour, so we come back 1:15. Here in this, well, beautiful, beautiful saal. Yes. Okay. Thank you, and see you back.